Let's learn how to handle work, energy and power in the. Now let's understand the three physical quantities work, energy and power. Prior to doing that, we must learn how to multiply two physical quantities which have a direction. Quantities which have a direction are also called as vector quantities. We all are familiar with multiplying two numbers which would give us an absolute value. On the contrary, when we multiply two vector quantities, we may end up having different results. This is simply amazing. We have a mathematical tool to do this called the scalar product. When we have two vectors with an angle theta between them, the product of the vectors a dot b will be ab cos theta, which means the magnitude of a multiplied by the magnitude of b multiplied by the cosine of the angle between them. Ultimately, the scalar product gives us a number. Let's also familiarize ourselves with the properties of scalar product. Scalar product follows commutative law, which means a dot b is equal to b dot a. Also, scalar product obeys distributive law, which can be written as a dot b plus c equal to a dot b plus a dot c. Interestingly, when we multiply a vector by a real number lambda, it would allow us to do a multiplication like this. A dot lambda b will be equal to lambda into a dot b, where lambda is the real number. A more interesting thing has to be learnt. We now would consider a unit vector along x, y and z directions, which would be represented by I, j, k vectors. If we multiply I with I or j with j or k with k, it would result in a value equal to 1. On the contrary, if we multiply the unit vectors I, j and k alternately, it will result in 0. That is, I dot j or j dot k or k dot I will result 0. A surprise awaits if we analyze the relation for rectilinear motion under constant acceleration a, which is v squared minus u squared equal to 2as, where u and v are the initial and final speeds and s is the distance traversed. If we multiply this equation by m by 2 on both sides, we will have half mv squared minus half mu squared equal to mas or f into s, which follows from Newton's second law. If we extend this equation to 3 dimensions by using vectors, the equation reads v squared minus u squared equal to 2a dot d, where a and d are acceleration and displacement vectors of the object respectively. Again, if we multiply both sides by m by 2, we will obtain half mv squared minus half mu squared equal to m into a dot d, which is equal to f dot d. Now this is a very interesting equation because the left hand side gives us the difference in the kinetic energies and the right hand side is the product of displacement and the component of the force along the displacement, which is otherwise called work. So finally we arrive at the equation Kf minus Ki equal to W, where Kf and Ki stands for final and initial kinetic energies and W represents the work done. This is amazing because it clearly shows that the difference in the kinetic energies will appear as work. Otherwise, work is done by a force on the body over a certain displacement. So to conclude, let's summarize the work energy theorem, which states that the change in kinetic energy of a particle is equal to the work done on it by the net force. Let's summarize the learning now. If we multiply two vectors resulting in a scalar, then we need to use scalar product rule. The resulting value may range from 0 to a maximum of the product of the magnitude of the two vectors. Next, work is simply done if force is applied in the direction of displacement. Else, there are chances that no work will be done. Finally, the change in kinetic energy of a particle is equal to the work done on it by the net force.